So we're going to talk about what might actually be our first useful topic in interference. So double slits are more of a scientifically important thing, but thin film interference and then in the next lecture, the Michelson interferometer, they actually have some practical value and you can do interesting things with them. So we'll start by just showing you thin film interference, and you've seen it before. So these beautiful patterns on a soap bubble, you may have wondered like what causes them. Is it something in the chemical nature of the soap itself, or something else? And then maybe you've seen what could be an oil slick. In fact, this could be a little bit of oil mixed in water, bad. Or maybe a little bit of antifreeze in a parking lot. Or it could be soap that's run off of your car when you try to wash it. And no matter what it is, they all make these kind of neat, colorful psychedelic patterns. So all of these are thin film interference, and it turns out there's little to nothing you can tell about the chemical nature of the stuff that's in the water. What you're really actually seeing is the index of refraction and the fact that it's very, very thin. So if it's telling you anything, it's telling you the thickness of the substance, not its composition. So this is thin film interference. And to understand it, you have to understand something that you actually already know. Light reflects and light refracts. And yeah, we've been talking about that for weeks, so you guys know that light both reflects and refracts. But the important point to make now is that it's not one or the other, it does both. So here what you see is light coming in, laser light coming in at the top of this tank, going through air, and then trying to make it into water. And you can see the angle of refraction, and yeah, most of it makes it into the water, right? So, but what you also see is not one, but actually two reflections. So, this is the angle of incidence, as always, normal to that. This is the angle of refraction, and this is the laser light coming in. But notice here, this is a little bit of reflection that happens at the same time, always happens. And then actually down here, as the light tries to make it out of the water and back into the air, so maybe it's actually hitting the glass, I see a second reflection. So this is actually the basis of thin film interference. I've got one reflection, a second reflection, and it's not the refracted rays that we really care about, it's the fact that these two reflections are coming back out and maybe they hit our eye. So what is it about them that might actually cause an interference phenomenon? So if you look at this for a second, you realize, oh, this second ray at the bottom has actually traveled a little bit farther than the first ray. So just like the Young's double slit experiment, or the finite width of a single slit, is I have two rays and they've traveled different distances, therefore I can have interference. So this is how things would look in a, still really cartoonish, but here's a light ray coming in, and the light ray coming in bounces off of the air-oil interface at point A, and then a little bit reflects, a little bit refracts, and then makes it down to the oil-water interface at point B. Every time the light ray gets to an interface, what happens is it reflects a little bit and refracts a little bit. And so what we see here is at A and B we get two reflections, and so I get ray 1, which has bounced off of point A and gone to the eyeball, and what we call ray 2, which has bounced off of B and then also made it out of the air-oil interface a second time, and also makes it to the eye. And it has traveled this much farther. So ray 2 has traveled a farther path length. And, don't take this too seriously, because we've forgotten, or we never actually learned in the first place, an important detail. But you're like, I get it. So ray 2 has traveled a farther distance. If that extra path length is a full wavelength for red light, I'll get a little bit of constructive interference for red light, and I'll see a reddish fringe. If the extra path length that ray 2 has traveled is, 17 halves of a wavelength, I'll get a little bit of destructive interference, and I'll see less of that particular type of light. So white light comes in for some particular distance. Each different wavelength will either experience constructive or destructive interference at a particular spot. And so when I see red, what I know is that's where red light is constructively interfering. Okay, so that's the basic story. The thing that we are missing is that when you bounce a wave off of a boundary, which happens twice here, what you might actually do is you might flip the wave upside down. So there's an extra shift that occurs. But the essence of thin film interference is that you get two reflections, one off of when you're trying to enter the thin film, one when you're trying to leave the thin film, and those can cause destructive or constructive interference. So it's not total at all. What it is a mild enhancement of one particular color. So the next thing to point out is that you see a lot of soap bubbles and parking lot pollution, but an important thin film is actually air itself. So these are what are called Newton's rings, and you can see the really cool rainbowy effect of this actually. So so-called Newton's rings are caused by a thin film of air actually. So here I have a light ray coming down, and the light ray coming down reflects off of the glass-air interface at point B. So that would be my ray 1. And then it makes it out, bounces off of this interface, the air-glass interface from the lower surface. So you see two surfaces here and here. And then that will reflect, and that will be my ray 2. And what I can see is that this thing has traveled a bit farther than that. The second ray has traveled farther than the first ray. In this case, it's traveled a farther distance through air, not glass. But the important part is the thing that's thin is the thin film. So all of this other stuff, I mean, now that you've realized what's going on with light, you're like, yeah, but doesn't light reflect here? You're right. And doesn't light reflect here? You're right. Light reflects all sorts of different places. The one that we care about and the one that's causing this set of fringes and patterns is just the thin part. So that's the moral of the story, is there are reflections and refractions everywhere. When you identify thin film interference, the question is, what's the thin part? The part that's very uniform on the order of the wavelength of light. So in this case, it's not the curvy piece of glass, it's the air gap in between them. Okay, so I said this is useful. This is how it's useful. So what you can do is you can actually use this to measure, really remarkably small distances, because what you have is from dark fringe to dark fringe, this will be actually not even a full wavelength of light. This will be a fraction of a wavelength of light, because it's making a trip there and a trip back. So this will be half a wavelength of light difference in between dark fringe to dark fringe. So let's say that I put a thin wire in this side. All I really have to do is count the fringes, dark fringes, and each one will correspond to an extra half wavelength of light. We'll go through the details mathematically with a couple of problems. But so this actually is a really precise way of measuring thin things, which is why I said it's useful. And what you see here is this kind of neat scalloped pattern. What this is telling you is not the thickness of something inserted in between the two panes of glass. Essentially, this is telling you how flat these things are machined in the first place. So it's telling you how tolerant your glass is, which is, again, very useful. And this is using air as the thin film, so it's not a soap bubble. Okay, so let's go through the math, and then I'll show you an assumption, and then we'll talk about this phase shift thing to put in a detail that's missing. So again, we're going to draw ray diagrams, but remember this is an interference phenomenon, so what I really care about is, do I have an extra whole wavelength or two whole wavelengths? Okay, so I got an incident ray. First thing that happens is the ray bounces off of the air film boundary. And that's it. Part of the ray refracts. The ray goes into the film. The ray makes it to the film air boundary and reflects. Comes back. It actually reflects again. We don't care about that. But then ray 2, which eventually makes it to our eye, will refract out of the film air boundary and make it out. So the first thing to realize is that this thing has traveled an extra path length difference. Let's call this d, the thickness of the film itself. And let's say that this comes in with some angle. And it turns out that this is like kind of overkill if you're far enough away from the light. If the light source is kind of just behind you and far away, we won't really have to worry about the Snell's lawing or this angle. But just so you guys know, I'm not cheating. The thickness is d. What I can see from the trigonometry is that the cosine of this angle theta is equal to d over L, where L is the hypotenuse, the length this travels. And so L, the whole length that this thing travels on the way down and the way back, is d over cosine theta. So the total extra distance is 2d over cos theta. And what you compare this to is essentially the d sine theta in the Young's double slit experiment. So really, honestly, that's like kind of all we need, because now we can write down a condition. We have the extra distance that this thing has traveled, and if, we'll just call it 2L, is equal to m lambda for m equals 0. I mean, it's never going to be minus, because we just called it the extra distance, so just plus 1, plus 2, dot, 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 dot. That is to say, it's traveled a whole number of wavelengths. Then we have, yes, I heard you all in a chorus, through the force, constructive interference. And so that would mean a bright fringe. And remember again, this isn't total constructive interference, it's just constructive interference. And then likewise, if we had 2L, the extra path length difference, m plus 1/2 lambda, where m again equals 0, 1, 2, dot, 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 we would have a dark fringe. So this would be important for monochromatic light. If you shine white light on a thin film, you know, most of the things are going to be dark fringes. All you really notice is the partial constructive. Okay, so this is one of the two sneaky details of thin film interference. So one of the two sneaky details is that, what is this lambda? So we have air and we have the film. So the extra path length is happening when we're in this medium. So whatever the film is, soap, oil, what have you. So that's the lambda that we care about. So in fact, what this lambda is lambda film. It's not air, it's the wavelength when this thing is traveling its extra path length difference. So what this is lambda film is lambda vacuum, or essentially lambda air, divided by the index of refraction. So just be aware that the ray 2, yeah, it travels an extra path length, but it travels the extra path length in this medium. So we have to worry about the wavelength in that particular medium. And this is mostly what we'll talk about, the bright fringes, but be aware that there are dark fringes too. Okay. So what's also true is that for the most part, we ignore the cosine theta thing, and cosine of theta, again, the thin or small angle approximation, which is a great approximation if this film is like super, super thin. A thin film usually lets you make the small angle approximation, which says that cosine of theta, if you know what this means, it's a justification. If you don't know what this means, don't worry. The small angle approximation for cosine of theta is that cosine equals 1. So basically, in this case, 2L, or 2D, is m film. So I'm not really going to box equations for you guys, because there's a caveat about equations in thin films. And this is the thing that we haven't covered. In fact, the reason to not worry about those equations is because they're wrong. That was our first attempt at doing this, and we missed something that's not obvious at all. And what's true with mechanical waves is that if I reflect a wave off of a boundary, so actually let me go back and make a strong point out of this. Like, this is all wrong. It's not all wrong, but the final result is. Haha, you wrote it in your notes. So we have a wave and it's reflecting off of a boundary. Two things can happen. If it has a fixed end, you know, again, for mechanical waves, you can think about this as Newton's third law, is that the wave's trying to push up on the wall's pushing back on the wave, so it flips it. That doesn't happen here, so the wave gets reflected upright. This actually happens with electromagnetic waves too. And if I have an electromagnetic wave that's going from a fast to a slow medium, so N1 is less than N2, so this might be, for instance, air into water is an example of, this is 1.0003 as an index of refraction, that's 1.33, so that's small n to big N. This is what will happen. As it goes from fast to slow, the wave will be reflected at the surface, but then the wave will also be reflected upside down. So the electric field will switch. Whereas, for instance, here, if I went from water to air, this would be 1.33 to 1.0003, and I would not get a reflection. So what does it mean to reflect an electromagnetic wave? That is a great question. So let me draw an electromagnetic wave, and let me draw a reflection of that electromagnetic wave. So what you can see is for sinusoidal waves, these are not sinusoidal waves in the animation, this is just like a wave pulse. So reflection from here to here is the same thing as shifting this by half a wavelength. So this peak to trough, reflection makes me go from peak to trough. The other way to go from peak to trough, or think about it, is I'm just adding half a wavelength. So reflecting is like adding an extra effective half wavelength. And this happens anytime I go from optically fast to optically slow medium. So I essentially add half a wavelength. So incident wave comes in, this is now an electromagnetic wave. I've got air and I'm going to oil. So oil has an index of refraction of maybe 1.3 and change to almost 1.5. And if I'm going from fast to slow, what's going to happen is my reflected wave is going to be flipped. And the way that I account for that mathematically is I basically, to the extra path length, I add a half wavelength to account for the shift. Boy, that blue on red's pretty eye-popping, isn't it? If, for instance, I go from slow to fast, I get no shift whatsoever. So this is the missing detail, and now we can go back and fix our analysis. Okay, so this is probably where you guys are at. And this is the sad news, is that there really is no equation for a thin film interference, because I could have a variety of different scenarios. I could be going from light to heavy, back to light, so that would be air, soap, air, like a soap bubble. I could go light from heavy to heavier. That's actually in one of the slides. You just didn't realize it. That would be air to water to oil. I could go from heavy to light. I could go light to medium to heavy. I have a variety of different ways of doing this. So there is no equation. What you guys have to do is tell the story of the light and basically keep a running tally of all the phase shifts. So we'll do an example of that, and we'll do a couple more. Okay, so this time we're going to do it right, and we have basically a little bit of prep. So we have N film is 1.35, and we know that N air is 1.0003. Numbers don't matter. What matters is what's light and what's heavy. So what's the story of ray 1? Ray 1 just reflects. So ray 1 reflects off of the air to soap boundary. When we go from air to soap, what happens? Well, we go from low end to high end. So in fact, what ray 1 does is ray 1 picks up a half wavelength phase shift, because again it reflects from optically fast to optically slow. So air to soap would give me that half wavelength shift. Okay, so what happens with ray 2? Ray 2 travels an extra path length difference. In the small angle approximation, what that has is just 2D essentially. So it goes, these pictures like the Young's double slit experiment are really exaggerated to show you effectively what's going on. What's true is the length that this thing actually travels for a thin film, again, is about equal to D. So we'll just call it D, the thickness of the film. And it also does one reflection, so there's no reflection back at surface A again. This is the only reflection. What happens at surface B? Surface B is a reflection from soap to air. And if I go from soap to air, what that is high N to low N. So we get no extra path length difference. Okay, so the effective extra path length difference for this, we almost had it right, but we forgot to include this reflection phase shift. So our total path length change is 2D minus the lambda over 2 that ray 1 got. So that's the effective delta R, right? This traveled 2D farther, down and back, basically 2 thicknesses of the film, but then ray 1 reflected, which gave it this lambda, it's a lambda over 2. So this is the thing that when this is equal to m lambda, we get constructive or destructive interference. Okay. And remember again that the lambda equals lambda film. So in this case, for this particular story, this is the equation that you would generate. If, for instance, if we flip this and this was soap to air, or we put oil here, which has an even higher index of refraction, I would get another phase shift and the formula would look different. So again, your job when you do thin film interference is not to remember a formula and know how to use it. It's actually to kind of generate the effective path length difference, including reflections where they need to happen. And again, we'll do some examples.